Let's now discuss about the solvent effect on SN1 reactions. In SN1 reactions, polar protic solvent is used. What is a polar protic solvent? See, if hydrogen atom is attached to a highly electronegative atom, like for example, OH as in water, NH in liquid ammonia. This way, if hydrogen atom is attached to a highly electronegative atom, we call it a protic solvent. Then what is the use of this protic solvent? It actually stabilizes the ions formed in step 1. Okay. We know that the polarity is measured in terms of dielectric constant. Right. In fact, polarity can be given as directly proportional to dielectric constant. Greater the polarity, greater is the dielectric constant. For example, if we take water, for water, the dielectric constant is 80. Okay. Now let us see how the ions are stabilized. Okay. See the cation, that is the alkyl carbocation formed, is actually stabilized by the interaction of the non-bonded electrons present on oxygen atom of the OH group of water. Let me show you that. See, this is the R plus or the carbocation, and now the water molecules with the non-bonded electron pairs. Now here, these are the interactions between the cation, the carbocation and the non-bonded electrons of oxygen. So this is how the carbocation is stabilized. Okay. Now let us see how anion is stabilized. See the anion, that is the halide ion or X minus, is stabilized by hydrogen bonding with hydrogen atom of the OH group of water, like this. The X minus. Now take the water molecules in this way. This is how hydrogen bonds are formed between the anion and the hydrogen atom of OH group of the water molecule. Okay. Now let us take the free energy diagram. Okay. See, the free energy diagrams, in fact, reflect the mechanism. We know that the first step is a slow step or a rate determining step. It can be given as now when I say slow step or rate determining step, obviously it will have the largest energy barrier. Okay. Now this is for the first step. Okay. It can be given as the first transition state or the one with the largest energy barrier. See, the height of energy barrier determines the threshold energy required. Because this is the largest energy barrier, this is going to be the slowest step of all. Now we can give it this. Say this is the activation energy needed for the reaction. This can be given as delta G1 for the first step. In fact, here itself we have shown the energy barriers for the second and third steps also. Let us take them separately now. one by one. Coming to step 2, it is a fast step, right? Now this can be shown take the same thing, highlight the second one. Now this is the transition state at 2, and this is delta G2. Okay. Now the third step. Even this also is a fast step, has got no much significance. Take the same diagram. Now the third one, this is TS3. And now give this. This is delta G3, right? So these are the free energy diagrams, with the first step being the slow step or the rate determining step, having the largest energy barrier. The third one being the fastest with the smallest energy barrier. Now the most important point. See, in case of SN1, secondary kinetic isotopic effect is observed. What is meant by the secondary kinetic isotopic effect? Look at this. Let me give you two examples. Okay. Now coming to these two, if we observe the ratio of KH to KD, it is about 1.2. Now let me say what the secondary kinetic isotopic effect is. You know, in this case, the site of bond breaking is this, right? This is a bond breaking site. In the rate determining step, If suppose the bond breaking site in the rate determining step involves the cleavage of carbon hydrogen bond, and if you find any difference in the rates, then we call that the primary kinetic isotopic effect. But here in this case, we are going to consider something other than the site of the bond breaking site. This is where we have considered isotopes. And see, it is a site other than the bond breaking site in the rate determining step. Now, if suppose the rate differs in this particular case in the site other than the bond breaking site in RDS, that is what we call secondary kinetic isotopic effect. Okay. Now let us go for SN2, nothing but nucleophilic substitution bimolecular. Okay. Let me give you an example. Methyl chloride with OH minus gives methyl alcohol and then Cl minus. Now let us see the mechanism of this. See, in SN2, the mechanism is concerted. What do you mean by concerted mechanism? Of course, it's a single step mechanism wherein the bond breaking and bond making occur simultaneously. Let us see how. Let me take a three-dimensional diagram. Initially, you know, the nucleophile attacks the carbon carrying halogen from the backside. Okay, so here the attack is purely from backside. Now this step, in fact, is the rate determining step or the slow step of the reaction. In fact, it is the only step. But the point is we get a transition state. Let me show you. Now look at the arrangement of bonds. Okay. Now the nucleophile that is coming in. I mean, this is a site of bond formation. Now say this is going out, a site of bond breaking. Okay. Now this, of course, can be given as double positive because you got two partial negative charges. See, this is actually called a pentavalent transition state. Look at this. See, the carbon here has got 5 valency with one bond going to get broken, the other one going to get formed. Because here, both the bond formation and bond dissociation, breaking and making occur simultaneously. That is the reason why we call it a concerted mechanism. Now, this simply dissociates. Chlorine goes out and OH gets connected. Now, look at the way the bonds are arranged. They have completely changed. Look at the way the bonds are arranged here, and then the way they have changed. See, this one, as and when the nucleophile attacks, say this one has gone like this, and this one, see, it has come here. It's just like an umbrella in a strong wind. Look at these two bonds especially. This one has gone here. This one has gone here. So this is how we can observe something like an inverted umbrella. And you know, this is what is actually called Walden inversion. Okay, because it was first, this kind of a mechanism was first proposed by Paul Walden. The configuration has changed. This is just like an umbrella in a strong wind. See, initially it will be like this. But when a strong wind blows, this goes here, this goes here, this goes here. That is what has happened. You can just check. So this is called Walden inversion. Very important thing. Now, let us see the characteristics of SN2. In this rate depends on the concentration of alkyl halide as well as that of nucleophile. It can be given as order with respect to alkyl halide is 1. With respect to nucleophile is 1. And the overall order of the reaction is 2. That means it follows second order kinetics. Okay. Next. These are all the differences between SN1 and SN2. Observe carefully. In case of SN1, rate was independent of the concentration of nucleophile, but here it is dependent on the first power of the concentration of the nucleophile. That is what I am going to explain now. Rate of SN2 depends on the concentration of nucleophile. Also, so a stronger nucleophile is generally employed. Okay. Whereas in case of SN1, what we have seen was a weaker nucleophile is sufficient. In fact, the solvent itself acts as nucleophile in SN1. Now, see in the rate determining step or the slow step, in fact, the only step, there are 2 molecules participating. I mean the alkyl halide as well as the nucleophile. Both the alkyl halide and the nucleophile are participating. So it is bimolecular reaction. It is a bimolecular reaction. I mean molecularity is 2. Because in the rate determining step, you got 2 molecules participating.